SwayamPrabha. Digital India. Educated India.
To day 7 of our lecture series, and we'll basically now jump a little bit more into the high entropy alloys. This will give you a breather because looking at the frequency with which elements are used in most of the multi-principal alloys, meaning high entropy alloys, but also encompassing CCAs, so compositionally complex alloys, which are not necessarily single phase. We see here on top of this periodic table that some of these elements, the numbers indicate how often were they reported in different multi-principal element alloys at the time this review was written, 2017. And you see that there are some, they are all the transition metals plus aluminum, which are really much more abundant than any other elements. So this is related to the fact that there's a lot of Cantor alloys, so these cobalt, chromium, iron, nickel, manganese, and related materials. So based on this, people have maybe varied the composition and made a new high entropy system, or maybe added an additional component so that maybe you get a two-phase complex alloy, maybe having two phases, and each of the phases is in itself a high entropy system. This is very important if we later in a few minutes come to analyze which are the typical phases of solid solutions, because here you see that it's only a very small number of elements that are used heavily in making these alloys. And so it means that the structures these elements prefer are obviously, or maybe not obviously, but maybe you can expect that these will control also the phase formation in the high entropy systems that are done. When we look at this, and maybe this is not very visible here on screen, this is actually a box. And this is another one. So we have, again, many high entropy systems which are made of 3D transition metals. And they are the most abundant when you look in literature. Refractory CCAs and refractory high entropy alloys are much less abundant, much less investigated. So there is a lot of work to do in terms of their microstructures, phase transformations, mechanical behavior, diffusion behavior, all of these aspects. And then there is rather a small number of, for example, precious metal CCAs, so making a high entropy alloy or a compositionally complex alloy just based on the precious metals. This is, for example, if somebody wants to make a new catalyst and wants to leave out certain very rare precious metal, then people are trying to use the high entropy concept in order to make a replacement with similar properties but less cost. And then also low density CCAs based on just elements which have a low density by themselves are also there, but not in abundance. So there is not many of those reported in literature. And so if you are going to make your own high entropy material, it's probably to look into the similar elements which have been used so far, because there is a reason why these are abundant. And that's because they can mix easily to form complex solid solutions, because they have rather similar properties. And we discussed already that there are different conditions, different conditions relying on different properties in terms of stabilizing complex solid solutions. And this mixing enthalpy as well as the difference in effective atomic radii in solution are the two most important, I think. And so the similarities in these properties between the different atoms and different atom pairs control whether you can easily make a solid solution or whether you will probably find formation of an intermetallic phase, which most of the time is to be avoided. This is the phases or number of occurrences of phases, different phases. And as you can see, FCC is really the most abundant one. And you know that BCC and B2 are closely related. B2 being an ordered phase with BCC structure. And all the others are rather rare. The sigma phase obviously occurs often, but you see it occurring often because it will form at the lower temperatures in many of these FCC high entropy materials. And yeah, these more complex structures are very rare, and often they form also as precipitates in given high entropy systems when they are needed at lower temperatures, so that they go from single phase to two phase or more multi-phase structures, especially decoration of grain boundaries, of triple junctions, and so on. This doesn't work well. So this is not related to the fact that FCC or BCC, this is my opinion, have special structures, but because the elements which we use in order to make these solid solutions, where we have to find elements which have similar properties, are favoring FCC or BCC structures. And this is, I think, why we see these phases in abundance. So there is no magic about these structures, FCC or BCC. It's just what people in the literature call structure in, structure out approach. It's a very hand-waving concept where you basically say, I take in alloying elements and they have in their natural single element case a preferred structure. That's the structure in if I add this element. And this will most likely, especially if I add several elements that prefer or have the same structure in, will result in structure out in the phase or structure of the phase of the solid solution that forms when mixing them. And so this structure in, structure out kind of thinking seems to be fulfilled for many high entropy systems. Even though I mentioned yesterday already, for the Cantor system, for example, it's not that the majority of elements in their natural form would be FCC, but still the similarity with in between these different elements is there. And nickel, for example, is a good example of something which really strongly prefers FCC structure. And so this approach seems to work. So one can probably, when you think of trying to make a high entropy alloy with a specific structure, and you think about choosing which elements to choose, think of the radius in solution. How is the mixing enthalpy between this element you might choose to add to a given number of elements to make a solid solution alloy? And is the crystal structure, especially close to the melting temperature, of that additional element also close to or even identical to the crystal structure which the other alloying elements form? If that is fulfilled, this is maybe an excellent choice for trying whether you really get a solid solution. So you see, alloy design in multi-component space is still relying a lot on estimating things and having some experience. But these empirical rules, which do not really have a good physical foundation, are working. So a working approach is never to be sneezed at. So this is what one can easily do. And this is also confirmed if we, for example, look at the comparison between experimental observations of phase content and estimated content. Observed content means either experiment or Calvert simulations, and estimated content is this structure in, structure out approach, which you can do in experiment, but which you can also do based on Calvert calculations. And you see that basically this grayish line is lying in between these different data points. And here for Calvert, there is two sets of data given. There's this factor FAB equals 1 or FAB equals all. And basically that is meaning that number, the fraction of data sets which have been accessed of the binary A-B systems which make up your 5-component system. So if all the 5 binaries have been really thermodynamically accessed, meaning completely calculated by Calvert and confirmed that reality is the same as the Calvert calculation, then the FAB would be equal to 1. So the fraction is 1 means all of them have been assessed. And if you take also smaller numbers, like maybe out of the so many binaries, only half of them have been accessed, then the FAB would be 0.5. And you see that yeah, obviously the fully accessed ones are the ones which are better, because then you really can predict, and Calvert is working great, so you can rely on the outcome of Calvert calculations, as you can nicely see when you compare these here. But if not all of the binaries have been accessed, then obviously there are larger deviations possible. All in all, the structure in, structure out approach works. Now, when we yesterday were talking about conditions for selecting elements to bring together, to mix in an alloy to make a higher entropy system, we were talking first about this these delta values for the mixing enthalpy of the solid solution, delta HSS. And then we have to compare it, obviously, to the formation enthalpy of intermetallics, which are possible inside of the system. And you see that they are comparable, but that on average the formation enthalpies of intermetallic phases in these systems tend to be a bit more negative, which means this is the hard job for the entropy of mixing to keep up and prevent intermetallic phases from forming. And this is why at the low temperatures in all of the high entropy systems, you expect additional phases to form. Sigma phase is one example. So this will be, I think, a general trend and tendency. Your friend can be that the time for forming these intermetallic phases at the lower temperatures might be very long, because the diffusion coefficients of the elements inside of these materials is very low, and you need diffusion, you need atomic mobility for the phase formation to occur. So it means the comparison with these predictions is a little bit difficult, because you never know ahead of time how long does it take. So it means when you compare now a calculation with your experiment, you have just made the alloy by maybe some melt cooling process. Now, at which temperature do you compare? Close to the melting temperature, probably you find the solid solution. A little bit closer, maybe still solid solution. Still a little bit closer, well, maybe you still see solid solution, but maybe if you wait 1 hour, 1 day, 1 week, 1 year, you could see it's a two-phase alloy already. But this timeline, how long do you need to anneal? This is something you can only infer when you have done diffusion measurements, or when you do very complex, long time annealing treatments, but then you never know when to stop, right? So the real correct time to pick for these experiments is very difficult to estimate ahead of time based on data, unless you have diffusion data. So it means you could have waited for 3 months, which is a long time already when you do a PhD thesis, but maybe it should have been 6 months. You will never know if you don't try, or if you don't calculate the rate, the kinetics from diffusion data. Yeah, again, looking at some of these empirical correlations, delta H mix, and this omega parameter I introduced, you see that it works very well. So the complete solid solutions are always in the upper left corner. And these are basically the high entropy systems which were predicted to form. And you can see that in the same plot you can also include solid solutions which are non-crystalline, metallic glasses. And there in the literature we have very similar concepts which have been introduced many decades ago, and they have been reformulated not so long time ago by Professor Inoue from Japan, but it's basically still going back to old rules by Turnbull, who did this in the 1950s and predicted there in the 60s, which ratios of properties would favor metallic glass formation, because at that time it was still not yet confirmed that you can make metallic glasses. So it's basically the similar concepts, and you see that specifically this omega parameter as a function of lattice, lattice distortion sometimes it's called, but it's more like the variance of atomic radii inside the solid solution works fairly well, because you have a nice separation between the regions where crystalline solid solution would form, or where amorphous materials form, or where you have intermetallics, or where you have CCAs in this two-phase region. So this, I think, are good. This is the omega parameter, you know, which combines. No problem. Good to ask always. Any other question concerning alloy design and how you pick constituents?
Like cancer calculation means we are plotting shell plot of phase property, right, by which we are analyzing. So when you say that we are calculating with CalFAD and we are doing it, so which in CalFAD what we are actually doing?
Well, CalFAD basically means that you predict the free enthalpy, entropy functions of your mixture. Yes.
That will give all phases.
That will give, no, as I said, you have to put in the possible stoichiometric phases.
After that analyzing from the experimental data, we can give that.
Yes, or if you have some literature or you do yourself density functional theory calculations, because there you can just look at the energetics of different configurations like AB, A2B, A3B2 or so. This can be done on a fairly simple ensemble, let's say 50 atoms or so. And there you can easily converge into finding structures and their relative energies with respect to maybe a solid solution, for example. This can also be put into the CalFAD code, so you can have these virtual phases, I would call them, so they were only calculated, also put in. This is then ab initio informed CalFAT. If you put in experimental data, it's experimentally informed CalFAT, but better to do both if possible. You will still miss maybe some of the intermetallic phases, but they would probably have very complex or rather complex crystal structures, because then you need larger elementary cells, and this is computationally more costly, so people avoid to do that. But they would also form much slower, so the probability that these form is lower. So I mean, if you first to start with have an experimentally informed database for CalFAT, and then you calculate based on these phases which should exist, it's, I think, a very good start.
Then suppose during printing, during solidification, cracks will form.
Yes.
So that is also a possibility.
That is always a possibility. So then you have to basically change processing conditions. It's not related to the thermodynamics, it's just about intrinsic strains. So you maybe have to then think about how your cooling method is affecting the crack formation, whether you need some stirring, things like that, or whether you need to do maybe Bridgman solidification to avoid that, to get to more closer to equilibrium configurations, which avoids building up stresses so much. This brings us to preparation methods, and I think in general they would not differ much from what you do for conventional alloys. So if you want to make a high entropy system, even a good high entropy system, alloy selection, constituent selection is really the most important aspect. But they are chemically complex, so you have to think of putting different elements together. They have different, as an element, different densities, so you get maybe, you know, buoyancy effects, you get segregations, you could get segregations. So you always go through this iterative cycle, right? You try out a certain alloy with a certain number and type of constituents. You try to make it, you look at the outcome, you see, cracks have formed, or maybe segregations are there, and then you know, some improvement must be there. So maybe you go to a higher soaking temperature, you have to soak for a longer time, you have to maybe flip after initial melting several times so that you get basically the density differences leveraged out. And only by this, you know, repeating, improving, you can get the best alloy. Obviously, this is counter any industrialized process because it takes time and costs money. And this is the difference between doing fundamental research and industrially applied research. This is why industry doesn't like at all to go to new alloys and new compositions, because you have to go through the whole process and optimize all the parameters in order to get a good product. And this means that what you are doing in terms of alloy development is mostly done at research institutions, or maybe companies together with people in research institutions. But not only very few companies really do this themselves. In the next years, already here, but I think even more it will become important to have machine learning and experimentally as well as experimentally informed high throughput computations, but also synthesis in high throughput and analysis in high throughput. So by depositioning processes, you can do all libraries of materials on a single substrate. So you go from pure element to maybe Cantor in one go by just changing the deposition rates of different elements. The big issue here is how to relate thin film behavior to bulk behavior. This is not easy because you have additional stresses, you have a huge surface area, you have different diffusivities, you have maybe different quenching rates if you deposit the film, as compared to bulk processing. And so one has to be very careful there. This is done in abundance over the world, but I'm skeptical. Yeah, this is the typical general synthesis routes, and for high entropy systems, mostly mechanical alloying, these typical classical solidification methods, thin film depositioning methods, and in the middle, bulk casting and additive manufacturing are the ones which are used. So arc melting, you know probably. You also know? Okay, then I don't need to talk much about it. It's obviously a process which works very well. You just assemble different ingredients. You use a high power electron beam to melt the material while it's situated on mostly a water-cooled copper plate. And then you go through the liquid phase, and once you stop the beam or you take it away, then the material freezes again. When you did this yourself, what are the problems with this method? This is a very common problem, yes, that the copper diffuses into the material because the copper is water cooled. But if you go to very high temperatures of your ingot, if you maybe are melting high melting point materials, you will not prevent copper going into the material because the heat cannot be taken out so quickly. Then arc melting is really a difficult problem. If you don't want to have copper in your material, it's very, very tough, very difficult to prevent. So for me, that method is good for something like up to the melting temperature of iron maybe, but if you go higher, it is very difficult. Also, if you, what you rightly said, have components of very different melting temperature, it's also a problem because you will have selective evaporation of the component with the lower melting temperature mostly. It means the stoichiometry of the ingot you produce will not be identical to the nominal composition you put in. Also, this is indicated here, you get very complex microstructures because you have a rapid heat flow to the cold copper hearth, which means you have directional solidification, but not in a uniform direction, but basically spreading everywhere. And a very rapid heat extraction that favors the formation of a supercooled liquid. And when you have solidification in a supercooled liquid, you know that the solid-liquid interface can become unstable, which means dendrites can form. Then you get a highly directional and fractal crystal phase forming that often doesn't have good properties. What is your experimental approach to avoid this, to get the effect of this initial solidification microstructure out of your system? How do you process the material after arc melting to get a good material? I recommend not only to do homogenization treatment, but once you have melted the alloy several times so that you have compositionally homogenized the alloy, it's normally a good method to severely deform the material by rotary swaging or by hammering, whatever, and then do the homogenization treatment. Or maybe do homogenization annealing, then deformation, and then again relaxation or recovery annealing, because that will give you not only compositionally uniform material, but also microstructurally the material will be much more uniform, as if you do not include this mechanical plastic deformation treatment in between. This has a huge impact on diffusion rates, as we found out. So the diffusion rates which we measured without doing this intermediate deformation step was much different as for the material going through the full cycle I just described. Yeah, a very good method if you want to avoid these non-equilibrium artifacts is Bridgman solidification casting, which means that you basically pull the material from a liquid zone through a solidification zone and cool it, but cool it gently and not so quickly. So you have a control over the speed of the solidification front. And that gives you normally good materials in terms of equiaxed structures, non-dendritic structures, good sharp grain boundaries, and also nice dihedral angles or tetrahedral angles at the junctions of grains, as shown here. So depending on how fast you pull in this Bridgman solidification casting, you get in this high entropy alloy different patterns of the microstructure, and you see that the more fast you pull, and F would be D would be the fastest, you get the finest microstructure, because basically you allow the least time for the material at the high temperatures to form the local structure. It depends really on the alloy what you have to do, because sometimes you want these features here to be larger or smaller, and then it means that you can play with the solidification front velocity in this Bridgman solidification to obtain the microstructure which you like to have. In this alloys made by this, you don't need this deformation process in post-processing, because then you would destroy the microstructure, right? So you have already used a process that makes an optimized microstructure, and it gives you control over the resulting microstructures. Laser melting and laser cladding, very similar to additive manufacturing really, is basically you have some powder which comes through this nozzle, and basically you have then a laser beam which melts the powder at the place where you want it to form some material. So it's like a directed deposition, like we also have in additive manufacturing. Obviously, we have all the pros and cons as for arc melting here, because also rapid solidification, directed heat flow during cooling, microstructures that form are probably far from equilibrium. So again, one needs to do some post-processing treatment if you do not want, if you are not interested in this metastable microstructure. If you want to have a stable microstructure, you have to do some annealing, maybe even rolling and annealing in order to form a good equilibrium structure. And otherwise, it's often that you see dendritic type solidification structures, which again tell you there was a rapid solidification process and there was either constitutional or thermal undercooling, so the solidification front has become unstable, dendrites have formed. Yeah, this is maybe not so important. If you want to do powder metallurgy, you all know ball milling, and there are two general types. It's like tumbler or a Twitter ball mill. They just are different in terms of how much energy you put into your material, which you either blend or just severely deform. Whenever one does these experiments, one has to be aware of restrictions. This is typically a process that occurs far from equilibrium, right? Because you transfer a lot of kinetic energy from the balls or from the mill itself to the powders, which means that defect densities are exceedingly high. Local temperatures could become very high with associated very high cooling rates. So the whole material is in a non-equilibrium state very far away from equilibrium. And so you could get metastable phase formation, amorphization, and so on occurring. But also you always have some material from your mill or from the balls inside of the mill abraded and mixing with your original material. So it means that you can never avoid some of the impurities from the materials the mill or the balls are made of going into your material. If you're fine with this, or if maybe the mill and everything is steel-based and you have also an iron-based alloy, then maybe it's not such a big deal. But if on the other hand you don't want to have iron in your material, maybe use a different ball mill. There are some like based on tungsten carbide or so, and then you can avoid getting these mixing effects into your material. If we want to go for coatings, obviously there is a range of methods, and industrially more relevant are these three: sputter deposition. So we have talked about sputtering already, right? So you have like ions, in this case often argon ions are used, that impact on the surface. This is your target. Atoms are sputtered off that target, and then they are deposited on the substrate, which you normally control in terms of its temperature and so on. And so you form films. You can also use pulsed laser deposition by again using a laser to evaporate from target and then deposit on the substance. Or you could thermally evaporate different materials in these diffusion cells, Knudsen cells, and then basically have a small pinhole so that you can direct a beam onto a substrate, and then depending on how many sources you have, you basically can mix different alloys. And something like this is done in this rapid throughput, high entropy studies in experiment, because here you have then, if we do a plane view of the substrate, you can basically have a shutter going also over your sample, and so you maybe start up with a pure element, then you have a binary, ternary, and so on. So you have really a library of materials brought onto a single substrate. Now you can use maybe some automatic transfer, not even breaking the vacuum, putting it into an X-ray machine with microfocus X-ray device, which can only measure in certain regions. So you can get structural informations over the whole range of compositions in an automated way. And then it gets more complicated. People are thinking also about looking at, for example, doing EDS automatically in an ESM on these, and SEM on these structures, maybe even going to TEM level. So far I have not seen it, but people were discussing this. So you get the full information, or rather a large range of information. You could have nano indentation also done automatically on already a huge range of compositions and never breaking the vacuum. This is important. Point is, problem with thin films comparing to bulk structures again, right? So this is valuable information for thin films, but how to really extract valuable information for your bulk alloys is something we have to always worry about, because it will depend also on the specific material under investigation. Additive manufacturing is very hip these days, and everybody investigates it. It is basically similar to laser cladding, right? I mean, you can not only use lasers, you can use all kinds of energy sources in order to do the additive manufacturing. I think most people using high entropy materials use this laser-based processes, powder bed fusion. So you basically have a powder of your material you want to make a structure out of. You put it down in a layered fashion, and then you scan with a high power laser in the regions where you want to create a structure. It melts, it freezes, and you take the rest of the powder off. You can even reuse it, and only the structure is created in positions where it should be. So you don't need to machine out material, especially for high cost materials like high entropy alloys. This is a favorable way to go. And let's see if this works here. No, unfortunately not. Well, this was showing the process. Okay, thank you. Can I do it like this? Sorry, on my laptop it worked, but here it seems not working. But basically, it's showing you this setup how the laser, because this powder is then distributed. Powder is distributed along this direction. Then this slider goes back with this one lowered. It basically scrapes off the power which is too much. It falls here into this container so that it's not wasted. And then basically the laser comes down and melts the powder in the regions where it should be melted. And then the next powder is applied and so on. And so you build up these structures, as you can see here. Problem here is that you cannot avoid obtaining structures which have a very, very anisotropic microstructure, because the heat is extracted in this direction, a little bit in this direction, and a little bit in this direction, but mostly in this direction. And the next layer will again deposit heat, and the next layer, and the next layer. So it means you will always see the tracks of your deposition melting. And you will also see the outcome of the heat flow. And that gives you a very, very complex microstructure. Also with a lot of defects because of the rapid shrinkage and rapid solidification. So you introduce a lot of strain because of shrinkage going through the liquid to solid transformation and due to the cooling. And that means you create strain, which can also introduce huge dislocation density. So the strain is actually large enough to go above the elastic limit into the plastic regime. And this is a highly defected structure which you get. So it means that when you want to use it, you probably have to do some post-processing, which is against the idea of additive manufacturing, because you would like to take the part and put it into your device, but this is probably not going to happen. This is not only true for the for the high entropy systems, but also for others. Yeah, and again, different ways of either directed energy deposition, so you don't have a powder bed or powder bed parts. And in principle, they all have the same benefits of making materials without having to machine them in much strong way afterwards, but also all of them suffer from creating non-equilibrium structures. And depending on the increasing constitutional supercooling, which is proportional to So it's really related to many of the processing parameters, like how do you deposit the energy, how much of the energy do you deposit, and how much time you give the system to either melt or cool. You will get additional different constitutional supercooling. Normally cooling speed is proportional to supercooling, and then you get from planar equilibrium structure something which is more related to Bridgman solidification, to something which might be very dendritic, which is similar to what you get in arc melting or laser cladding. And obviously one does not like to have very dendritic microstructures. But yeah, this is what you typically get in microstructure evolution of an AM, additive manufactured processed high entropy system, and that's actually now a two-phase high entropy system. It's a eutectic high entropy system. And you can see that the microstructure variation is quite large, right? So the properties of this material would depend a lot on whether you look at the properties in transverse direction or building direction, because of these non-equiax structures that form. So you have elongated grains, you have dendrites which form. So it can be messy in terms of the microstructure you get from additive manufacturing. And one needs to really always analyze also the microstructure in all three different directions in order to get a full image and full picture of what really is the microstructure of the material. Just doing a planar cut through the microstructure like you normally do, polishing and look at the cross-section is not enough. You have to look at three cross-sections which are perpendicular. Now, we also thought that single-phase and multi-phase high entropy alloys, while multi-phase is not really a high entropy alloy, this is why it's in parentheses. So single-phase and multi-phase compositionally complex alloys are important to look at, especially because for properties and property optimization, more and more it's recognized that a single solid solution phase will not fulfill all the needs. And we can use all the tricks we have learned from conventional alloys to make properties better also in high entropy systems by having second phases forming. Important is what I already indicated, that we then have to worry about the formation enthalpy of the intermetallics. And they shouldn't be too much different from the mixing enthalpies of the elements when they form a solid solution phase. Because otherwise they will dominate and only this, and then all the residual ones will form. And this is not what you're going to have. A reminder again to what was suggested by Ye when suggesting high entropy systems first. When he compared the thermodynamics of systems, considered solid solution which where the mixing properties have calculated as if they were an ideal solid solution. It means mixing enthalpy 0, mixing entropy only the statistical part, like how many configurations you can get by mixing 5 different types of atoms. And he compared it to an intermetallic compound in the same material, which was perfectly ordered. In a perfectly ordered intermetallic phase, the formation entropy equals to 0, because all the atomic positions are defined. Obviously, then you can get more easily by calculation the stabilizing effect to be strong, just based on the number of constituents you mix in a solid solution, right? But this is not a realistic approach, because this is not realistic. And this is also not realistic. So a good system which approaches the mixing enthalpy to be equal to 0 for binaries is copper nickel. But still there, we have a slight positive enthalpy of mixing, and low temperatures, it has now been confirmed that there is a miscibility gap. So spinodal decomposition will occur when we go to sufficiently low temperatures and wait then for very, very long times. So again, this is difficult, and this is what can happen, right? I mean, if we only place 3 different types of atoms onto a common lattice, so we form a solid solution, then different processes can occur. If we have slightly higher mixing enthalpy, positive mixing enthalpy, then we can, in the solid solution, get spinodal decompositioning. This means it basically forms 2 different solid solutions, different in terms of their chemical compositions, because the system would tend to go to these 2 compositions. We could have the situation that energetically it's more favorable to have more than 1 solid solution present. So this would be something like eutectic. High entropy alloys. So you have 2 phases that coexist together, and both of them have multi-principal alloying elements. You could get to intermetallic and solid solution forming 2-phase equilibria. So it means CCAs would be this type of thing. If the formation enthalpy, the magnitude of the formation enthalpy of the intermetallic is too high, or we could get a high entropy alloy as a single phase solid solution. And all of these possibilities depend just on the thermodynamic quantities, but the thermodynamic quantities also depend on atomic radii, which are effective values, and depend on electron concentrations and so on. When we now think of dual phase high entropy alloys, this is something which I think is more new, especially in iron containing systems, sometimes iron based systems. These studies have been like a continuation from steel-based research, because if you think about steels, some of them actually have rather large concentrations of additional elements in addition to iron, and all of them have a high number of functional constituents. So typically like 10, 12, 13 constituent elements, which each and every one of them has its own function to make higher strength or higher ductility, higher work hardening rate, and so on. And one aspect here which people emphasize is that in these 2-phase, dual-phase high entropy systems, they can also get transformation-induced plasticity TRIP or twinning-induced plasticity TWIP effects. And this is what you can find in these high specialty steels, which are very expensive. So there you pay by kg and not by ton. But this is what saves your life, for example, if you drive an expensive car too fast and you get an accident. Because these mechanisms can absorb huge energies, and this transformation can occur very quickly. So it's also a process which occurs at the high strain rates. And this is why this is so beneficial to use materials which can show this type of effect. Obviously, microstructure gets more complex, right? Because basically you have now different phases, and the phase content also depends on your processing conditions. So if you deformed it heavily, then basically you undergo also some of these transformation-induced processes. And so it means that you need to account for their reversal by, for example, temperature exposure for a longer time. That they are very beneficial can be seen here. So this is engineering stress, engineering strain. And you can see here's a nice dual phase high entropy alloy which consists of FCC and HCP. By the way, are FCC and HCP related? Yes, exactly. It's a stacking fault, right? It's a different stacking sequence. So you go from AB, AB, AB to ABC, ABC, ABC. And that just makes a transformation. They have both the same packing density. And this is why this process can occur so quickly, right? Going from FCC to HCP. And it's basically, when we think of how twins originate, this is coming from the stacking fault, right? So you create the first stacking fault, and then when the second stacking fault goes along the same plane, I mean the same plane direction, but a parallel plane, then you basically have a twin, mechanical twin. And this is how this twinning-induced plasticity works. And when you see this curve here, so let's say this one here, what would you say are the benefits if you have a material performing like this with respect to the other curves shown in the same graph? High strength, exactly. Which one? Yeah, it is less ductile, right?
In the third one, I think the phase transformation can happen during the first one, like FCC plus SCP, no phase transformation. Like the rest of them, like I have it. Strain hardenability is also higher.
Very good. This is very important. The strain hardening rate . So it means the material also gets more strong when it is actually needing to be more strong. Under the deformation, under the mechanical stresses which are externally applied, it reacts by becoming more strong while not failing in a brittle way. And this is actually why these materials are so good. Right? You can really train them so that they have this very high strength, high strain hardening rate and capability. And this is lying then in the microstructure, and in this case there is also a trip effect because the martensite is formed during the deformation, and this is while it's adding. Why is actually a phase formation helping?
Absorbing shocks. They oscillate to martensite. They are absorbing shock, trip effect.
Yes, the transformation is driven by the mechanical energy, so it's transformed into a microstructure feature. Also, following dislocations have a problem passing the phase boundary between austenite and martensite, right? So this is also helping them and increasing the strain hardening capacity of the material. Another dual phase alloy system is or are eutectic or eutectoid high entropy alloys, sometimes HEAAS, termed as HEAAS in literature. And obviously you know what a eutectic is, so it's the same concept, right? But you just don't have pure phases, materials A and B, or A and some intermetallic compound AB, AX, BY on both sides of the eutectic, but here you would have multi-principal phases which make up this eutectic structure. And also there you have many beneficial properties, especially in terms of the mechanical properties, so high strength and good ductility, because of many phase boundaries which you are having in the material. So here you would not have a transformation-induced plasticity, but you have a dual phase eutectic microstructure. Which microstructures do you know in eutectic systems to form? Yes, you can have rod-like, you can have lamellar, you can also have dendritic, and all of this is basically what you also get in eutectic high entropy alloys. Depends again on how you design the system in terms of composition and how you design the process going from liquid to solid and doing or not doing post-processing treatment. And you can nicely see some of the eutectic features which you get are really very, very much as textbook-like, right? So you wouldn't see from the microstructure that these are high entropy alloys, right? So it means all of your knowledge which you have gained from the AB systems, binary systems, you can directly transfer to high entropy systems, even to complex systems like eutectic high entropy alloys. So there is conceptually absolutely no difference, just that the compositions are a little bit more complex, but in terms of formation, mechanism, and so on, you can directly use your knowledge which you have gained in the introductory classes. Yeah, it is in terms of the mechanical properties, right? Because you see here that you get something like a very high strength, very long work hardening capability with high strength again and good ductility before failure or elongation before failure. And this is something which is really beneficial, because some of these materials are also, like you see here, copper, aluminum, titanium, vanadium, on the more low density side. So you can make material which have lower density as material which have similar performance, but still having the same or similar mechanical performance. And high entropy systems always have this tendency that they can be used up to a little bit higher temperatures, because the microstructure stability tends to be larger. So it means it could be, but this is active research. People are not, and I also am not quite sure that this is true in all cases in general. So you could design materials which have lower density but higher working temperature. And yeah. And then these are some relationships about different, again, criteria and where to find E here, so the eutectic high entropy alloys, as compared to other competing phases which are typical in these systems that form eutectic high entropy alloys. The quintessence of this is, delta H, delta S work nicely, otherwise systematics are poor, but statistics are poor anyway, because there are not so many eutectic high entropy systems which have been reported and investigated so far. So far as of today, these are the important criteria and conditions if you are looking for eutectic high entropy systems. And if you think of making a eutectic high entropy alloy in a material where nobody has done it before and where you are not sure that the eutectic high entropy system can be formed, people are using these so-called network approaches. So you start from binaries or ternaries, and you know basically when you start out from, let's say, start simple with a binary. And then you know when you add nickel, you go to a ternary eutectic, right? So then you again know that iron and chromium with this, or if you would use chromium, you would get another eutectic. And this is why chromium and nickel have the same tendency for the formation of a eutectic, starting from the binary, and then iron is basically added without knowing it beforehand. So it means that you basically go from known eutectics, and then you add from binary to ternary constituents where you know that the eutectic is likely to form. Then you go to the quaternary, then you go to the quinternary. So it means it's like a network in that sense, that you go from eutectic to eutectic to eutectic, and you always increase the dimensionality of your alloy system. And this is, again, how people empirically look for and try to find compositions which are eutectic high entropy systems. And this is maybe also the most recent development in high entropy systems, I would say, that you now go for eutectic high entropy systems where both phases are a high entropy alloy. Since it's most recent, not much is really known about their properties. I mean, these few mechanical tests and so were done, but otherwise it's an open blank field. So there's much room for investigations, I would say. Nothing is known about corrosion properties. We don't really know microstructure property correlations for these systems. So all of this, I think, needs to be developed in the coming years. And yeah, the simple way of thinking here is that when you basically have your eutectic high entropy system, that you have the same microstructural approach and the same correlation microstructure to property as for a binary eutectic, right? So you have a matrix or stable solid solution phase and an intermetallic phase that forms, but that intermetallic phase is also in itself high entropy alloy. And then basically you go through that. Any questions about material selection, phase selection, element selection, what we discussed so far today? Yeah, I mean, yes, in principle, yes. You can have any phase there is, and I think per definition, as people use it in the literature, just having high entropy alloy as one constituent, one eutectic phase, one lamella phase, let's say, and maybe line compound even of only two elements at the other phase would also be a high eutectic high entropy alloy. But the true sense of the meaning, and I think the most interesting properties, will be if you have a multi-constituent phase for both phases of the eutectic. You could have a Lavis phase which has all 5 elements of a high entropy system. But as I showed you initially with these number of phases reported for high entropy systems, the number of those known is very, very small. So one has to see if one wants to design such a thing, is there already a reported high entropy intermetallic in this structure you want to have? And then maybe this is the more important criterion to select your constituent elements. So you start from there, from the more complex to form phase. Then you maybe add 1 or 2 more components to give you the opportunity to form also a solid solution phase in addition. The nice thing about this approach, if you have a complex, structurally complex phase and a solid solution phase, is that probably you have a very nice effect of having a rather soft and deformable phase, as well as a rather strong and not so easy to deform phase. So it means that according to the composite model, to calculate mechanical strength for a composite material like a eutectic, it would give you maximum strengthening. Because of the fact that the interfaces are attached to each other, there is like a constraining condition for defect formation. So crack formation is not so easy. So even if this strengthening intermetallic phase is intrinsically rather brittle in nature or has a low elongation to failure, it might have a much longer elongation to failure if it is part of the eutectic microstructure. You need to worry then a lot about grain boundaries and triple junctions, because there the symmetry is broken. So it means these are then the typical places where crack initiation would occur. And then one might use some strategy based on minor alloying with additional element that goes and segregates to the boundaries and also to the triple junctions then. And that could act like a grease to prevent easy early crack formation between grains. Highly complex and a little bit conceptual and not very direct, but I think, yeah, there's very few studies on such approaches, and I think it could be very valuable, especially if you go for alloys which either have low density or have an additional functionality where the price per kg is not so important. Like, for example, some magnetic behavior or maybe usable as a catalyst, something like this. Good. So let's maybe start a little bit with volume diffusion in single phase high entropy alloys. Sluggish diffusion, one of the core effects. This is the original plot, which basically was published in order to show that the hypothesis of sluggish diffusion is correct. Now, when you look at this, you will not see any sluggish diffusion, because it's a comparison of the different constituent diffusivities as a function of temperature in the Cantor high entropy alloy. So equimolar 5-component high entropy alloy, single phase solid solution. Why do you not see sluggish diffusion? Because sluggish could only be meant as a comment which is done in comparison to what? So sluggish compared to what, right? And I will show you later that this is not so easy to define. Very importantly, these were done by diffusion couple experiments, right? So it means there were 2 blocks of material. both of different composition, placed together, annealed, and then basically the constituent element distribution has been investigated across the former interface. Right, so we have an interdiffusion flux of elements which are driven by chemical diffusion, by the gradient in chemical potential. This is not self-diffusion because there is an additional force term, force in terms of non-equilibrium thermodynamics, which is given by concentration gradient or gradient in chemical potential, to be more accurate. Now, when we look again in the same paper, we see this comparison. So these are the diffusion coefficients in the system for the different constituents, the 5. Yes?
These are plotted for FCC crystal structure.
Yes, all of this is for FCC solid solution.
If you change the crystal structure,
It will be much different, yes. What would you think?
yeah, it will change because like BCC element will not go easy in FCC.
Yeah, but here you see the nice thing about the Cantor alloy is we have several elements in there which are not FCC, but the whole thing at sufficiently high temperatures is completely FCC.
But at room temperature,
At room temperature, different, yes.
like at a high temperature means maybe what?
Yeah, this range here, right? I mean, above something like 950 Kelvin or so, the solid solution phase is stable at equimolar composition. But if you go to lower temperatures and wait for a sufficiently long time, you will see additional phases to form. But here they have confirmed that it was a single phase solid solution.
But here it will form the same thing like BCCR down FCCR.
Yeah, I mean, in all these temperatures here, single phase solid solution. But if you go to lower temperature, absolutely other phases form. Sigma phase.
But diffusion like sluggish means like
Yeah, it means from this plot we don't know what it means, right? We need to compare. They have done this, and this is shown here. So these are the constituent diffusivities made or derived from an interdiffusion experiment, and then compared to, so this is always the diffusing atoms. Right, and this chromium, for example, atom, its interdiffusion was measured in different matrices, so in different host materials. So the question asked for the experiment to answer is how fast is chromium diffusing in nickel, in FCC cobalt, in FCC iron, and in these alloys, and then it is compared to the high entropy system. And this is done for all 5 elements. So we have self-diffusion of nickel in nickel, and we have impurity diffusion of cobalt in nickel, and so on. Here, how do you measure nickel diffusion in nickel? Only by tracer diffusion, right? So in one plot, interdiffusion and tracer diffusion results are compared. This is very complicated, or actually, in the way it is done here, not correct. Yeah, this is complex. Therefore, the comparison shown here, which always shows that this blackish dark line, which is the measurement in the higher entropy system, is lower than all other lines. This was taken as the reason to say, yes, we confirm sluggish diffusion is happening in high entropy alloys. But it's very inaccurate to use this graph for this comparison, because you compare different diffusion coefficients, which are not the same, which must be different because of their physical definition. And also, if you look at it, the difference is not large, right? And we compare here single elements as a matrix and maybe ternaries, and then we go to 5-component, which means you would expect some change in any diffusion coefficient to happen if you change the alloy system, when you have more disordered lattice occupation and so on. Also, if it is within 1 order of magnitude difference, like in most cases here, it's very difficult to say, because you have an error bar also, which is not shown here. So it means, I would say this is not proof for sluggish diffusion. Right, so one needs to do better. They also have shown here a plot, which is the diffusion activation enthalpy, which they name Q. And it's normalized by the melting temperature. And it's plotted for the diffusion of these elements in the different matrices, right? So this is again the diffusing element. And these are the matrices. Again, the question the experiments answer is, how large is the diffusion activation enthalpy, let's say, of chromium in pure iron, of chromium in pure nickel, and so on. And you see the activation barriers, and they are normalized by the melting temperature in order to compare these different matrices, pure elements, up to the high entropy system. And you see the pure elements are colored in red. The binary ternary alloys are colored in green, and the high entropy system is colored in blue. And when we compare it, then we see that the blue bar is always the highest. And this suggests by the authors that basically higher activation enthalpy for diffusion means more sluggish diffusion. Would you guys agree? Would you say this plot confirms that there is sluggish diffusion in high entropy alloy? Well, diffusion is many jumps, right? At what temperature? Yes, But you would say it's an Arrhenius representation, and the activation enthalpy is taken from the slope. So as long as the temperature dependence is the same Arrhenius dependence, then Q is a given value for a certain range of temperatures. It could not be too high a range because then the mechanisms change, but within the given range, you would say there is one Q, one activation enthalpy for this type of diffusion process which is dominant in the material. But still, when you think of how would you write a diffusion coefficient equation as a function of temperature dependence with Q as the activation barrier? We see often in diffusion measurements that diffusion processes where actually the activation enthalpy barrier can be higher still are the processes which show faster, higher diffusivity. And this is because the prefactor is also important, this d naught, because that's a function of probability of doing the jump, how many alternative and analogous direction of the jump is there, how probable is the back jump with respect to the forward jump, this and how often is it attempted per second. This all goes into this prefactor, and this is sometimes the ruling factor. So it means that even though a process has a higher activation barrier, so it should be slower, but if it has also a higher prefactor and even much more higher, then still the diffusion process can be faster even though the activation barrier can be larger. This is specifically the case for some processes where, for example, in a substitutional diffusion process, the vacancy binds somehow to the atom which diffuses. So it means the process of the jump is quite large, but the vacancy will always be closely by. So the probability of finding an empty space is then very large. And this can then give rise to these counterintuitive relationships of having higher diffusivity even though the activation barrier is higher. So this is again not any confirmation of that diffusion is more sluggish in high entropy alloys. Forgetting that all this data was obtained by the wrong type of experiment. Good. Then I would like to stop here.